Welcome. In this video, we're going to talk through some spectrophotometry related problems. So we're going to start out thinking about a lab that we did in class, the analysis of brass, where we analyzed a blue solution. It was blue because it contained aqueous copper ions. And we observed that this blue solution absorbed light with a wavelength of 630 nanometers. And using the spectrum below, we can see what color of light that is. So notice how 630 nanometers, that's right around here. So that is orange light. So if a solution appears blue, it is absorbing orange light pretty well. And a general rule of thumb is that when a solution appears one color, that means it's absorbing the complementary color. And by complementary color, we mean the color opposite it on this color wheel. So notice how a solution that appears blue is absorbing orange light really well. If it appears yellow, it's absorbing violet light really well. So keeping that in mind, I'm going to be able to answer some questions. What color of light would a green solution absorb? And if you haven't answered these questions yet, please pause the video and try these on your own and then restart it to check your work. So a green solution is going to absorb red light. That's the color across from it on the color wheel. If a solution absorbs light with a wavelength of 470, so 470 would fall over here. So if it's absorbing blue light, what color would it appear? Well, it would appear the opposite color. It would appear orange. And a yellow solution, if it appears yellow, that means it is absorbing violet light. So somewhere in the 400, 430 nanometers. So it looks like this would be our best option there. One more related question here. So here's a scenario where someone's using spectrophotometry to determine the concentration of red dye in a mixture of dyes. So we're assuming the solution contains both red and blue dye. And we take a look at the absorbance versus wavelength graph for both red and blue dye. And we can see right here that the red dye is absorbing light well at around this wavelength, close to 500, whereas the blue dye is absorbing well around here, around 630. And there's not a lot of overlap here. So red absorbs well here, whereas blue has almost no absorbance there, and vice versa. So if we were testing a sample and we wanted to figure out how much red dye is in the sample, we want to pick a wavelength of light that red dye absorbs really well and blue will not absorb. So we want to pick something at around like 500 nanometers, because at 500 nanometers, our red dye is going to be the only substance that's absorbing any light. The blue will not be absorbing. Okay, so here's something else we want to think about with Beer-Lambert law is, or this equation is called, we're seeing right here, is known as the Beer-Lambert law. And it tells us that the absorbance, which is A, is directly related to the concentration. So as a concentration of a solution increases, the absorbance will also increase. And if we were to plot this for a given data set, and you put concentration on the x-axis and absorbance on the y-axis, we should end up with a nice, really linear line. The slope of this line is going to vary based on your sample and what wavelength you're using. And let's write this relationship out again. A equals epsilon BC. In this relationship, A is absorbance is the y-axis. Concentration is the x-axis. Therefore, this value right here is the slope of the line. So we can use this graphical method with some experimental data to find the slope, which is the value of epsilon times B. But coming back to this simple question, when the concentration of the solution increases, the absorbance will increase. So it is a direct relationship. The more concentrated, the greater the absorbance. So let's look at a calculation application here. This is similar to what we did in the analysis of brass lab. So we have a 2-gram sample of bronze. Bronze is an alloy, which is a mixture of different metals. So it's got copper along with some other metals. And we want to figure out how much copper is in the bronze. So we the student makes a calibration graph by measuring the absorbance of various concentrations of copper solutions. And notice how we have this nice linear graph here. And then the student then takes their sample of bronze, which is our unknown. We don't know how much copper is in the bronze, dissolves it in nitric acid, and then dilutes it to a volume of exactly 100 milliliters, measures the absorbance, and observes the absorbance is 0.3. So first we want to determine the concentration of copper in the solution. On this graph, they didn't actually give us the slope. So for this one, instead of using our equation like I mentioned over here, we're actually just going to estimate in this example. So we're just going to use estimation strategy. Other times, if we're given a slope of a line, we'll be more precise and we'll plug it in our calculator. But for this one, we're going to say, okay, the absorbance is 0.3. So that's right here on our graph. And so if we kind of look at it out here, we'd say, okay, that's going to intersect with right about here. So it looks like our concentration is between 0.1 and 0.2. So our concentration is 0.15 molar. All right, so that's the molarity. Now let's find moles. So remember, molarity is moles per liter. So if I want to find moles, I would take molarity times my liters. My molarity is 0.15. My liters is, well, what's my volume? My volume is 100 milliliters. So I have to convert milliliters into liters. And this is one thing you do need to know is your metric prefixes. We do need to know these conversions. That milli is like 1,000 there. So since 1 liter is 1,000 milliliters, that means 100 milliliters is 0.1 liters. You do not have to show your work for this type of conversion, but you can if you want to, if that just helps you to make sure you're doing it correctly. I'll show it once as an example. So you got 100 milliliters and 1 liter is 1,000 milliliters. But I am okay if you can just jump straight to there, that's fine. And so in moles, that is 0.015 moles of copper. So remember, that's what this is graphing, molarity of copper. So that's moles of copper. And then we want to find the mass percent of copper. So to find the mass percent, I first have to find the mass of copper. So I got 0.015 moles of copper. To find the mass, I'm going to take my moles times my molar mass. There. And I will find that I get 0.95. I think I only have 2 sig figs in this. 0.95 grams of copper. Okay, that's how much copper was in my bronze sample. Now let's turn that into a percent. So to find the mass percent of copper, I'm going to take my mass of copper divided by my mass of the whole sample. That's the bronze. So the mass of the copper is what I just calculated. It's 0.95 grams. The mass of the bronze sample, we weighed that at the beginning of the experiment. Looks like it is 2 grams. I'm going to multiply it by 100 to make it a percentage. And I end up with, when I round it to 2 sig figs, I believe I get 48%. So our sample of bronze was 48% copper by mass. Here's another graph. These are some questions from the AP Classroom. There's some College Board style questions. You'll see several of the spectrophotometry questions are essentially kind of error analysis type questions to really see, do we understand what's going on with this technique? And this one is kind of wordy, so we're going to read through what this is telling us. So diagram 1 is showing us pure acetone, and acetone is the solvent in this scenario, meaning it's the thing that you dissolve in. So we're doing an experiment here where instead of dissolving something in water, it seems like we're dissolving it in acetone. And then over here on the right, diagram 2, this is a solution where you have some sort of solute. They don't specify what the solute is, and it is dissolved in acetone. And this is our unknown. We're trying to figure out the concentration of it. And it tells us when the student reads the absorbance of the solution at 280, the result is too high. So which of the following could be responsible for this error? So the first thing I'm going to do on my graphs, I'm going to look and see where is 280. So over here on this graph 1 with acetone, it's right around here. And I'm going to notice that's interesting. There's a little bump here. So it seems that acetone absorbs at 280. So that's interesting. And then over here, it's also where the peak is over here with my solute on the right. And so let's look through these different options and see which of these would result in an absorbance reading that is too high? Okay, so option A, the student added too little solute before measuring its absorbance. So if you added too little solute, that would result in a solution that is more dilute. And a solution is more dilute if it's less concentrated, it's going to have a lower absorbance. So this source of error would result in absorbance being too low, whereas this telling us the absorbance is too high. So A doesn't work as an explanation here. B, they rinse the cuvette with the solution before filling the cuvette with the solution. That doesn't seem like a source of error. That just seems like good practice. They're making sure the cuvette is filled with the appropriate solution. So that doesn't seem to really work here. C, the student forgot to calibrate the spectrophotometer by using a cuvette containing only acetone. This one looks promising. So what could have happened? Notice how we're seeing the acetone is absorbing at 280. And so if we were to zero our spectrophotometer using acetone, then we could basically kind of account for the fact that acetone is absorbing here and kind of remove that and essentially zeroing out our spectrophotometer and saying, okay, let's ignore the absorption from acetone and just focus on our desired solute. But if the student didn't calibrate it, so if they didn't zero it out using acetone, then they would end up with a little bit too much absorbance there, because when they measure the absorbance, they would see the solute absorbing and the acetone absorbing as well. So this one seems like the right answer, but let's double check. Look at D. Option D says the setting was accidentally changed from 280 to 300 before they made the measurement. Well, let's look at the graph. If someone had changed the wavelength to 300, notice how it actually absorbs less at 300. So this would be a source of error, but this source of error would cause us to get a lower absorbance. So that would not fit our data set. So C is the right choice. It's that acetone is making our absorbance level too high. So that's our source of error. Let's look at 9. 9, we've got a sample where we're making a nice calibration curve with different solutions of cobalt, and we're measuring their absorbances. And we see that one data point is too low here. So we're trying to explain what is going on with this data point. Why is it too low? So we're looking for, like, why is the absorbance low? Option A, there was distilled water in the cuvette when the student put the standard solution in it. That sounds like a good possibility, because if there's extra water in the cuvette, that's going to make our concentration lower, which is going to make our absorbance too low. So that seems reasonable. Let's check the other one. So B says, what if we accidentally put in a little bit of 0.1 molar in with the 0.5 molar? That would cause some error, but this error would make our absorbance go up because our solution would be more concentrated. So that doesn't fit with what we're observing here. C, the student used a cuvette with a longer path length. Well, here's where we can, what's the path length? We can look back at this equation here. A equals this epsilon BC. And this value right here, the B there, is our path length. And we'll notice that if the path length increases, so if B is larger, our absorbance will actually be larger. So this would be a source of error, but this error would make our absorbance too high. And what we're observing is our absorbance is too low. So that doesn't seem to make sense there. And the student did not run a blank between each sample. That's not something you really need to do. That wouldn't cause that error necessarily. All right, last one here with some error analysis. We've got another discrepancy we are trying to explain. So if we look here, whoops, at this data set, trial 4 doesn't seem to fit the pattern here. Okay, so what we notice here is, like, as you double the concentration, the absorbance doubles. Double the concentration, the absorbance doubles. If you go from trial 2 to trial 4, if you were to triple the concentration, we would expect the absorbance to also triple, but it does not. This absorbance is too low. It's lower than it should be. And so I'm going to find an explanation that would fit this. So option A tells us that maybe the solution was at a lower temperature. We have not seen any information about how temperature might impact absorbance. That seems very questionable. I'm going to put a question mark by that. All right, the measurement was made using a different spec that uses a cell with a longer path length. So again, path length is that value B here in this equation. If the path length is longer, the absorbance would actually be too high. So this error would make the absorbance too high, but what we observed is the absorbance is too low. So this error does not fit with what we're observing. C, the solution was saturated and the flow of light was restricted. Flow of light was restricted. That sounds like it has a really high absorbance. That means a lot of light's being absorbed. But that also doesn't fit with what we're observing. We're observing absorbance is too low, so C doesn't make sense. How about D? The concentration of the solution was actually lower than 0.15. That sounds reasonable, okay? Because if this solution actually had a lower concentration, then its absorbance would be lower. So maybe somebody made a mistake when making the solution. The concentration is not actually 0.15, it's something lower. That's why this absorbance point doesn't fit in with the rest of our data. So the answer here is D. All right, thanks for watching. Let me know what questions you have.